Nucleophiles, adding the carbonyls. Aldehydes and ketones don't have a leaving group. Or do they? The oxygen of the aldehyde or ketone can ultimately become a leaving group. Okay? We introduced the I tried to give you a broad overview on the green sheet. Non-reversible reactions, which we did already. All right. Nucleophilic addition to the carbonyl. Game over though. You can't reverse, nothing else is going to happen, you just protonate. Since this is a strong base, you can protonate water or acid. And that's it. We typically get an alcohol. Like adding the Grignard to a carbonyl or aldehyde ketone, no leaving group. Methyl comes in, electrons up, and then we protonate. The original H is still here, yeah. If this was an acid derivative, we would have a leaving group, like a chlorine or a OR group or something. All right? No leaving group. And we can also have these reactions down here. These are reversible. Because anytime you make a pi bond and kick off a leaving group, that's easy to do. Here, the nucleophile can turn around and be a leaving group, where above it cannot. We can also protonate and get a product like above. That's possible too. But in addition, the oxygen can end up being a leaving group. And so the original carbonyl oxygen is now gone. Okay? This is possible when the nucleophile has a lone pair, the way it was like a nitrogen maybe. Alright, so I tried to give you an overview there. We'll be continuing there. The white handout, there's a lot of applications, warm up. It also includes the nomenclature, which is by video. I posted that video a couple of days ago. There's also some review of NMR, of aldehydes, ketones. It's really nothing new though. It's sort of something that's been here for a long time. But the way I cover that stuff now, you've seen it all. Okay? But it is review, no charge, no extra charge for that. A lot of applications. We may or may not have time to hit them all. But to me, they're pretty important. That's why I give it to you. To make the chemistry that we're doing relevant, to see the applications. Okay. Green sheet. We did some simple additions. Aldehydes, ketones to make hydrates. Hydrates are not stable. Most of them are not. There was one here that is stable. Anybody have a reason why this one might be stable? Called chloralhydrate. Also, if this dehydrated, what would it form? This lost water. You should expect that this could lose water. What would it form? It would give that aldehyde, right? Yeah, how'd we do? Right, good? Okay. But this is going to hydrate, plus water. Simple addition. Water adds electrons up, and you get a proton transfer. You can do that acid catalyzed or base catalyzed, or you can just do it with plain water. Okay? Most favor aldehyde ketone. This one favors the hydrate. Why? Any particular reason? Chlorines. Okay, makes some sense. Why? The chlorines are very electron withdrawing. Okay? Very electron withdrawing. If you were chlorine, would you rather have the molecule exist like this or that over there? So there's 3 chlorines there. They're like ruling, we're going to exist like this. Why would it prefer to exist like this? Because chlorines are very electron withdrawing. Here the carbon is sp3, but here it's sp2, yeah? Everybody agree? Which carbon can the chlorines pull more from?
SP3.
The sp3 carbon. sp3 carbon is actually known to be a donator. These greedy chlorines love it because an sp3 carbon is more willing to loan it some money. Here, take the electrons. Okay? An sp2 carbon is like, hold on, chlorines, don't be pulling on me so much. And the chlorines are like, okay, well, let's just favor this structure then. Now you're going to be willing to pull. Okay? And so the dipole, the polarity, which is a big thing, I think it's kind of like physics. Okay? Electrons moving a certain way, they're able to move more this way. Make sense? At least that's an argument. Okay? So that's that one and those kind of like that. The strong withdrawing groups actually promote the hydrate form over the carbonyl form. Then we look at cyanohydrins. So cyanohydrins you can isolate. You can actually isolate them. It doesn't mean they can't reverse. Everything under this heading can reverse. And if these reverse, what are they going to release? Well, anytime you make a pi bond and kick off a leaving group, can you kick off cyanide? Yeah, we said that's easy and fast. We said if you've ever seen it be minus, you can kick it off here. Have you ever seen CN be minus? Yeah, that's cyanide. Yes. You're going to kick it off, and then the cyanide will come back and take the H from the positive oxygen, and you're just going to do this. This is driven by entropy. One molecule becoming 2. This can happen. You're going to release ACN, and then that's quite toxic. An alternative to using ACN for making them, we looked at KCN. By the way, one of those on my board, cover sheet has a nice, one of the best I've seen is KCN, Sunshine Band. Take a look at that. Very nice. That supplies the cyanide. This is an acid which I don't think we've used before. Instead of H2SO4, it's just a mono acid. Monosodium salt. Still has one H remaining, and it still can be acidic enough to do acid catalyzed stuff. The thing about this is a solid, where H2SO4 is a liquid. So you got 2 solids there, but there's your cyanide, there's your H plus source. There you go, cyanohydrin. How about this? What if we then treat this with aqueous acid and heat? What could happen there? Any chemistry could take place there? How about that there? What do we do?
You reduced a nitrile?
No, that's not reduction. Not a reduction.
Isn't that what we just went over though?
You hydrolyzed the nitrile
Hydrolyze.
to the carboxylic acid. Yeah. Reversible, right? Nitriles can be hydrolyzed to carboxylic acid. Any acid derivative can be hydrolyzed. Yeah? Final exam is coming soon. Final exam can be anything. We don't just focus on test 4, but we have to be aware for anything. What type of chemistry can take place? Now, if this alcohol was on some other carbon, we might do an elimination there, but you can't eliminate that alcohol. There's no place to put a double bond because there's no beta hydrogen, And so you're not going to do an alcohol elimination, it's just not possible here. But some other alcohol you possibly could. Okay? So we have to be ready for final exam when it's going to be comprehensive organic 1 and 2. Toxicity of cyanogenic glycosides. I think it's in the white handout. Page here, you can read about it. I mentioned the pit of a peach, so-called stone fruits, actually contain cyanohydrins. Now, most people don't eat the pit of a peach, and even if you did, your body might not be able to break it open to get in there and to get this stuff. But we'll see this later. Cyanogenic glycoside. Glycoside is a general term for carbohydrates. Here's carbohydrate, and it's a cyanide here, cyanogenic glycoside. It's in the form of an acetal. We'll see acetals in just a minute. Acetals can be hydrolyzed. That's reversed. But when this chemistry takes place, it produces a cyanohydrin, because that's going to be liberated. And then the cyanohydrin can further break down into ACN and the aldehyde there. And so that's just kind of showing that. But there's a little reading about it, and it's basically an application, and also understanding glycosides, carbohydrates. You'll be seeing that a good bit in biochemistry. There's sugar groups. Okay. Here we go. B. If you remember, A I call simple additions. Now B, by analogy, we could maybe say not so simple additions. Well, the only difference is, simple is we don't do something else. Here we're going to lose water. Here the carbonyl oxygen will eventually be lost as water. So we're going to kind of keep going a little bit. Example 1 is formation of acetals. We do have a variety of new functional groups to know, such as amines, acetals, hemiacetals, hydrates, which we saw. Okay, so some additional nomenclature that may be in addition to the nomenclature video. You see some new. This is an acetal. Okay, we can make acetals from aldehydes and ketones. Remember, anytime I give a compound, it's aldehyde or ketone. This just happens to be a ketone. Ethanol, H plus catalyst, and we can get this. What is an acetal? It's a carbon with 2 OR groups. OR, OR. What if this was, instead of 2 ORs, what if it was 2 OHs? What would that be called?
Hydrate.
It's a hydrate, okay? That was last time and reviewed. This is where instead of O, it's 2 OR groups. The hydrate can come from that ketone. The acetal comes from that ketone. You should see which ketone that came from here. Okay, how did we get here? It's almost like a diether. But it's not called a diether, it's called an acetal. Question?
How do you name, why is that named acetal?
That's just a name. It's just a common name.
Okay.
There's a little bit, why do you ask?
Isn't ACE what we usually do for like a methyl coming off?
Acetyl? Yeah.
So it's like, would it change?
Right, I see that, and it's not, that's maybe why you question. Also, the AL ending, if you watch nomenclature, is for aldehydes. It's not an aldehyde, so there is some, you're right. It's not that intuitive. This doesn't really tell the name that much. Yes. Okay, how are we going to do this mechanism? Carbonyl chemistry, acid catalyst. What's the first thing you want to do?
Protonate carbonyl.
Protonate something. What do you want to protonate?
Carbonyl.
Carbonyl, yes. And so we can protonate carbonyl. This here. What next?
Have ethanol add.
We have ethanol. Ethanol can add nucleophilic addition to the protonated carbonyl. Electrons up, that becomes OH. That's there, that's his O. We need to draw this out. Ethyl. Okay, nucleophilic addition. Now, if this was water, we would just remove proton and we would have our hydrate. We're going to lose this oxygen here. We don't want to lose this oxygen because we're not going to lose the R group from the oxygen. It's possible, but it's not happening here. We're going to do proton transfer. And instead of having this oxygen protonated, we're going to have this oxygen protonated. So there's the O-ethyl. Now that's there. And this is protonated up here. We transferred the proton. Now at this point, anytime you make a pi bond, particularly using a lone pair, you kick off a leaving group. We have a lone pair here to make pi bond. We have a positive oxygen, which is a great leaving group. Even for a fast step, I mean, it's going to be very, very fast. I mean, this is going to give, this is double bonded here. I'm just going to call the ethyl group R, or propyl group, carbon, methyl. Now this is double bonded oxygen. I drew my bond angles more appropriately there. This oxygen still has an ethyl. One lone pair left, and that's a positive charge. And we just lost the water, which we said we would form. Okay, this thing cannot lose an H to go neutral. Doesn't have an H. Also, we see its two equivalents. At this point, another ethanol. This is like a protonated carbonyl. It's just instead of an H on it to make it positive, it's an ethyl. Nucleophile comes in again, move electrons to the oxygen. I won't worry about bond angles quite yet. That's ethyl, that's H, that's plus. This down here is what? Oxygen with ethyl. And now what on the oxygen?
2 lone pairs.
2 lone pairs, right? What does this arrow mean? Electrons coming back. Everybody here? Yeah?
Mm-hmm.
And what do we need to do to get to final product?
Have the catalyst take the H.
The only thing we have to do is give up the H plus again. What was the catalyst? Maybe it's sulfuric acid. Maybe it was HCl. I'll do that. It'll just be a small atom. Cl minus takes the H, leaves the electrons behind, and we're going to reform our catalyst. That is it. I just got both O-ethyls drawn up, where in this structure one O-ethyl is up, one O-ethyl is down. It's the same thing. That carbon is not chiral, so there's no stereochemistry to have to show. Is this reaction reversible?
Yes.
Yes, ever since either it's B or Roman numeral 2. What is it? It's on the first page. We're under Roman numeral 2 for the remainder of the handout, I believe. Reversible, yes. That is, this mechanism is completely reversible. If you had an acetal, could you protonate one of the oxygens with a strong acid?
Yes.
Sure, and you would get here. And at this point, could this lone pair come in and kick off that positive oxygen? Sure, that would give you this. Here, instead of ethanol adding, could water add to this? Yeah, it's no difference, ethanol or water. If water added, you would get this. At this point, could you then do a proton transfer from this oxygen to this one? Yes, why not? At this point, could this lone pair come in and kick off that oxygen? Yes, why not? You would get this. And then you just take the proton from this and you're back here. This reaction is complete equilibrium. We have to drive this. If you wanted to drive this to the acetal, how would you do it? We've talked about this before. Add what? You do it like it just, instead of using two equivalents, that's just what's necessary. Very often you would just dissolve it in ethanol, use ethanol as solvent. You have a huge amount of ethanol that would drive it that way. What's another way to drive it?
Remove the water.
Remove water as it's formed somehow. Could you boil the water out? You're doing this in lab. Could you do it and boil the water out?
No.
Boiling point of ethanol is about 78 degrees. Boiling point of water is 100 degrees. If you tried to boil the water out, the ethanol is going to go out first. So you can't do that in this case.
Do you put a hygroscopic to absorb the water as it
You could put something in, maybe sodium sulfate would, there's things called molecular sieves, which pull water out. And once it absorbs it, in fact, even though it's still in the flask, it's effectively removed from the equilibrium because it's just been absorbed and it can no longer do anything. You have to drive it. Just like the Fischer esterification. Completely reversible. If you had an acetal, how would you convert it back to the carbonyl? Which is hugely important. You guys usually cannot see that if we hydrolyze this, what does this reverse back to? You got to know what carbonyl it reversed back to. And I guarantee you there will be problems with that. Because it requires looking at it more than a microsecond. All right? How would you drive it back to the carbonyl compound? Lots of water. So you just use like aqueous acid. Lots of water and drive it back there. This thing will fall apart with lots of water. Okay? But if you get rid of the water, somehow, you can drive it. A lot of times here you have to actually get rid of the water. Question?
Well, I was just saying, like, so couldn't you just boil the ethanol out as well in this case? Because now the boiling point is lower.
Going the other way,
Yeah.
you could perhaps pull the ethanol out.
But if you used excess acid, wouldn't it remain protonated?
Would what remain protonated?
Our last product there.
The carbonyl
Yes,
compound?
sir.
It all depends in practice. If you extract it, it will no longer be protonated. Because acid-base equilibrium is very, very influenced by practical methods that we can't always talk about. If I tried to explain it, I'd have to spend an hour explaining. Because this is not a strong base. And so it's not going to completely react and make a isolatable product with a strong acid. We can protonate that in a mechanism, but you're never going to protonate it and form a salt with it and isolate it. If it was an amine, you could, or something strong. So the complexities of acid-base equilibrium in practice there's a lot there. It comes from just experience. Okay, this is an acetal. Along the way, we had this structure. Now, I didn't go neutral completely here. I just did a proton transfer. Well, we never went neutral here. But let me just show you something here. This is actually a hemiacetal. What does hemi mean?
Half?
Yes, it's a half acetal. Ever heard of half acetals? Yes. Basically, it's one alcohol on the carbon and the other's an OH. Now I've got it protonated, but if you just want to draw that's a half acetal. Okay? If they were both OHs, it'd be a hydrate. If it was both ORs, it'd be an acetal.
So why not a hemi?
Yeah.
I like to call it a half acetal because it just sounds nice. Better.
Not nicer.
Do what?
Not nicer. It doesn't sound nicer.
Okay. Well, you get what I mean. It's halfway to an acetal. It's called a hemiacetal, but hemi means half. Right? Okay. So that's what a half acetal is. You don't like half acetal?
No.
I didn't say I don't like it. It just doesn't sound nicer.
Heavy hydrate compound.
Sounds like when my son's trying to get out of chores or something. You know?
Okay. Acetal. Now, a common well, much more common type of acetal is a cyclic acetal. Okay? A cyclic acetal. Here. What is a cyclic acetal? The two OR groups are actually, they're both bonded to carbons, right? So it's R group, but they're connected. And so it's a ring and two oxygens are part of the ring on a cyclic acetal. This would come from using not two equivalents of a monoalcohol, but one equivalent of a diol. Okay? Now you should work through this mechanism, but basically you're going to get to a point where you have the half acetal, and it's going to be OH and OR, but the R group here has, it's a diol, and so it's got O and it's got that, right? That's your hemiacetal. And then you're going to continue on the mechanism, and then when you're ready to bring in your second equivalent of alcohol, well, it's already right here. All right? And so this oxygen ends up being bonded here. But you should work through it. It's the same exact mechanism. And then you end up displacing this oxygen, and when this bonds here, you have a green. These are very common because if we balance this out completely plus water, right? Because here, remember the problem using like ethanol or any other small alcohol which may have a boiling point below 100, boiling point of 100. Well, this is actually antifreeze, ethylene glycol, boiling point approximately 200. Toluene sulfonic acid, remember that dry acid? So here you can do the reaction at like 120 degrees or so. The water can be boiled out and removed, but you don't lose your diol because it has a much higher boiling point. And so a higher boiling alcohol allows you to make your acetal with boiling out of the water. Now acetals tend to be protecting groups. It's like, I don't care what the acetal actually looks like. We'll see that more than going forward. So I'm going to make one where I can use a higher boiling alcohol and I can just boil out the water, and it just is more convenient to do that. Questions? Okay, as I said, acetals can be protecting groups for aldehydes and ketones. That's sort of one of the biggest main uses of acetals. You don't often see acetals in drugs because the acetal, when it gets into the body, lots of aqueous acid, they're just going to revert back to the carbonyl compound. But on the warm-up question, I think there is maybe an acetal that is in a drug. Okay, let's look at this protecting group here. If we had this dicarbonyl compound, ester and ketone, how could we convert it to compound A? If we wanted compound A, in which what has happened here? The ester has been reduced. It's been doubly reduced. Additional elimination here gives the aldehyde, and then another addition ultimately would give the alcohol. But if you tried to make compound A this method, you would not get A. You would get the other compound over there because the hydride would also add to the ketone. Okay? Now you guys should see how both products are formed. I suspect that maybe everybody doesn't see that quite yet. Question?
Could we get to A through like a specific reducing agent? I mean, oxidizing agent?
We're going to get to A by the route I'm going to show you, using acetal as a protecting group.
The only reason I'm asking because isn't that kind of what we did in our second lab where we got like a specific
Use 2 equivalents of diol. No, attack the other one.
In the diol oxidation, we oxidize one alcohol, not the other.
Yeah.
Yeah. There's a million examples of that in chemistry. It's just, if you tried to do it, it wouldn't happen.
Okay.
You have to find the right conditions. Is it possible? Is there another way to make A other than the way I'm going to show you? Perhaps, probably. But what we're really looking here is using acetal as a protecting group, and that's what I'm trying to illustrate. There may be another way to make A. If you just try to react with LAH, you're going to reduce both groups. Hydride's going to react both, and you're going to end up with this product. You should see mechanism of how we get there. Okay? How can we make A? One way to do that is to first make an acetal of the ketone. It's going to be a cyclic acetal. Should show product. Now up above I used a 2-carbon diol. Here it's a 3-carbon diol. Yes. Also, the chemistry we're doing right now is aldehyde ketone chemistry. If this reacted with the ester, you would not get an acetal. Okay, you would get acid derivative chemistry, leading group chemistry. Okay? Aldehyde ketone reactions are different from acid derivative reactions. Well, you can sit down and do the mechanism and see you're just not going to get the same thing, and you should not get the same thing. Acetals are only made from aldehydes and ketones. This is an acetal reaction. It's going to react here to make acetal. Now you could say, well, why would it not react here? It possibly could. You could get chemistry here. Here's another broad thing. Aldehydes and ketones tend to be more reactive than acid derivatives. Now in this case, we have sp3 inductive donation to this carbonyl. What do we have going on over here? Resonance. Resonance donation is a much stronger effect. There's more electron donation over here than here. It turns out that this is your more reactive carbonyl. And again, aldehydes and ketones tend to be more reactive than acid derivatives. Except for acid chlorides. All right? That makes sense. That ain't an acid chloride. We never have an acid chloride here. But ester is a pretty less reactive acid derivative. Okay, we can talk more about it then. These are the types of things you have to sort of, as we work between acid derivative chemistry, aldehyde ketone chemistry. Acetal is going to react here. And we're going to get what? We get that acetal. All right? That's a 6-membered ring there. By the way, when we make an acetal, are we doing redox chemistry? How many bonds to a more electronegative atom does this carbon have? 2. How many bonds to a more electronegative atom does it have? 2. No redox. All right? An acetal is a aldehyde ketone derivative. Acid derivatives have 3 bonds to a more electronegative atom. Like that over there.
If that was like a 7-member ring, would that be too unstable or like?
It's possible. 5 to 6 are best. And more likely. Okay, at this point, now we can come in here with LAH. And that's only going to react here because acetals are not electrophilic. They're unreactive. Under non-acidic conditions. It's not a carbonyl anymore. You have to have acid to get this to react. It's like an ether. In that regard, it's like an ether. And if you remember ethers, we said they're very good solvents for basic reactions. Look back at the ether handout. Diethyl ether is used for like Grignard reagents. Okay? And there's no acid here. You can't have acid with LAH, you're going to have a fire. This is going to give that there. Again, you got to know how this comes from. This comes from hydride adding electrons up, back down, aldehyde, and then hydride adds again to aldehyde. And then where does the H come from? Appropriate workup. Now, at this point, how can we get A? Well, that's an acetal. Can an acetal be converted back to the carbonyl compound? Yes, we're under Roman numeral
Two.
2. How do you convert acetals back to carbonyl compound?
Water.
Lots of water. How do you drive it the other way? Lots of water. That's going to give you compound A when you do acetal hydrolysis. Now you also regenerate that alcohol. But that can be easily purified out at that point. Everybody good?
Couldn't you also protonate the acetal and the alcohol comes around and kicks off one of them and that protonates again, so you just have like an ether and 2 alcohols?
That is possible. This could act as a nucleophile here. Try to show a product. Let's look at it. And you can make maybe another acetal. But with lots of water, you can be driven to the carbonyl. If you did this with acid and no water, I could see this displacing that. Problem is that'd be the same thing, because when that gets kicked off, it's that would be 3 carbons, 1, 2, 3, OH, and that's only 2. This could end up going to a 5-membered ring where you protonate, this gets kicked off, and this oxygen ends up bonded here. You could work that mechanism. This is an example of using an acetal as a protecting group. We protected the ketone as an acetal. We reacted with some other group. Then we regenerated the ketone by hydrolysis of the acetal.
Instead of reacting with LEH and then an aqueous workup and then H3 plus, can you just do LEH and then H3 plus?
Sure, when you work this up, you're probably going to, yeah. You may not ever isolate this, because this workup here is probably going to be that, and with the workup, it's probably, you may not even isolate it. Okay, acetals is other protecting groups. You can also protect diols. Please look at this chemistry, what the problem is. What do we need to protect? Protecting groups are very common in organic chemistry because sometimes you have a group that's going to react when you don't want it to. And you can do a protection. You can protect it, sort of mask it, and then turn around later and kind of demask it or deprotect it. Regenerate it. That's kind of what we're doing here. Here's another example here for diols. What the problem is, how can we correct it? And this is sort of a big thing for acetals. Acetals are common protecting groups. Okay, guys, see some of you in lab this afternoon. Again, lab report, start thinking about that. Take a look at the board outside my office. You want to do something a little fun or unique with your cover page, your title. And have a good day, guys.
Oh, I just do the quarter circle.
Some people want to read it.
And then I just multiply it by 0.1.
You don't have to tell.
Because then the 0.20.
Okay, that makes sense.
We're not 0.20 higher than 0.20. Yeah.
The distance is.
Hi, Rich. That's about 20. Yeah, that's the angle is higher too.